Okay, it's recording now, and let me share PowerPoint. Oh wait, actually. Okay, yeah, so you guys should be able to see it now. All right, then let's get started. Okay, so today we're gonna, so it's the 13th recitation, and it's the last one of the semester. And today we're gonna be going over transistors and logic gates. So I have a few announcements. PA5, it's due tomorrow. And the graders for that are Neeraj and Azita, so you guys could email them if you have any issues. And PA6 should be out shortly. Okay, so starting with transistors. So microprocessors today contain millions or billions of transistors, and so these transistors are combined to implement logic functions, and then those are combined. Those are combined to build higher level structures such as adders or multiplexers and things like that. And then we could combine those to build the entire processor. And wait, let me just. I'm just gonna reshare. There's like an issue with this. Okay, are you guys able to see it? Okay, thank you. All right, yeah. So, yeah, so let's just look at a simple switch circuit. So we either have the switch is either open or closed. And when it's open, there's no current going through. When it's closed, current flows. And so this is basically like, we're just going to be building circuits now using transistors, and we're just gonna, it's either going to be on or off, open or closed, and that's either when there is voltage or no voltage. So would a program be able to select which logic gates to use? Not exactly. Like, I guess that would all happen as it gets encoded down to assembly and then down to binary. So I don't think you could like go ahead and choose which ones to use. And okay, yeah, so we have, we're going to be working with these N-type MOS transistors. And so we have two types, N-type and P-type. So first, let's go over the N-type ones. So in the case of the N-type, so when the gate has, so basically, this is kind of what the circuit looks like, or the transistor. And if you have a positive voltage going in, then the circuit is closed. And when you have a 0 voltage going in, the circuit is open. And in the case of P transistors, these are complementary to the N type. And yeah, so this has the opposite effect. So when the gate has positive voltage, the circuit's open, but when the gate has 0 voltage, the circuit is closed and a connection is made. And this will all start to make more sense as we go on. But basically, so if we think of it as digital values, we could either have a 0 or a 1, right? But in terms of circuits, it's how much voltage it is. So it's either going to be low voltage or high voltage. And so for the case of our 0, we could have a voltage between 0 and 0.5, which is considered a low voltage. And then between 2.4 and 2.9 volts is our high voltage, which represents our 1. And so these are typical values for the high voltages. And for our purposes, we'll just use 2.9 volts. But that's not really, it doesn't really matter for what we're going to do. So we could use these N and P type MOS transistors to build a complementary MOS circuit. And so in this case, we basically combine the P-type and the N-type together. And the P-type circuit gets attached to a positive voltage, and the N-type circuit gets attached to the ground. And so basically, when you have an input going in, it goes into both circuits. And if the input that goes in is 0, then so we just talked about how for P types, 0 voltage connects the circuit, right? So if the input is 0, this circuit will be connected, and in this case, the output will be a 1. And for an input of 1, this circuit will be connected, and the output will be 0. So this is kind of like a NOR gate, and it returns the opposite of what your input is. It just negates it. And yeah, so in this case, for any input that can go in, positive or 0, or high voltage or low voltage, we need to make sure that the output is either connected to the ground or to positive voltage, but it can't be connected to both for any given input. So let's look at this this inverter. And so this is basically a NOT gate, and we just discussed this. So I have an annotated version of this here. So we have a P-type gate, P-type transistor here, and an N-type here. And basically, so here the output is either going to be positive high voltage, or it's going to be 0 from the ground, right? And here's our truth table. If you put in a 0, you get a 1 back, and if you put in a 1, you get a 0 back. And this is the analog version of these digital values. And so let's take a look at this here. So if our input is 0, what happens? So we talked about P-type gates, right? So for P-type gates, they're open when you enter a positive input, but they're closed when you enter a 0 input. So, and for N-types, they're closed when you enter a positive input, and 0 when you enter, they're open when you enter a 0 input. So in this case, when we enter a 0 input, the P-type is going to be closed, right? But the N-type is going to stay open. And so if this is the only gate that's closed, then then the output is going to be a positive voltage, right? And so the output is going to be high voltage. So when we put in a 0, we'll get a 1 back. Or if you put in 0 volts, we'll get 2.9 volts back. And then in this case, if we put in a 1, the P-type will be closed. The P-type will be open this time because it's open for positive voltage. And the N-type will be closed because it's closed for positive voltage. So because the N-type is closed, it's going to go through here, and it'll connect to the ground, and the output will be a 0 from the ground. So that's basically how a NOT gate works. And then we could move on to NOR gates, right? So this basically, so you're probably wondering why we go from not to NOR instead of why don't we go straight to OR? So it's actually simpler to think of it this way because it's just you'll see in the next slide how we could go from NOR to OR, and it's just simpler to think about it this way. So let's say this is our NOR gate, right? This circuit over here. And so let's take a look at what's happening here. So we have two inputs. We have A and B, and they could be either 0 or 1, right? And both of these inputs are connected to this these serial P gates here, okay? And they're also connected at the same time over here to these parallel N gates. So, that's basically what's going on in the circuit. So we have the serial structure up top and the parallel structure down here, and both inputs are going into both of those structures. And let's take a look at our truth table, right? So for the NOR gate, for just like a NOR function, it only returns a 1 or positive voltage when both inputs are 0. So let's think about that, right? So let's think about that in terms of this circuit. So if both, let's say if if both of these inputs are 1, neither of these gates will be closed, right? Because these gates are closed for, these are p-type gates. So these will only be closed when the voltage is 0. But if we're given both ones, these will stay open, so we won't get a positive return. And when both of these are 1, these parallel ones will be closed. And it doesn't really matter which one is closed because they're in parallel. So if either one is closed, we'll get the signal from the ground. So our output will be 0. And so in any case where anything is a 1, either A or B or both, our output will be a 0 because both of these serial ones won't be closed. And because the serial ones aren't closed, so both of these have to be closed for the positive to reach the output. But that can only happen when both A and B are 0. And that mimics our truth table exactly. And for all other cases, both of these won't be closed, and either one or both of the parallel gates will close, and and then the ground will be able to reach our output here. So this is just an example here. If A is 0 and B is 1, this P-type gate will close. This one will stay open. So the positive one won't reach the output. And and then in the case of A being 0, this ground one, this stays open, but this one closes. And because it closes, the 0 is able to reach the output. So now we're going to go from a NOR gate to an OR gate. And so in that case, so we just learned how to make a NOT gate, right? And then we learned how to make a NOR gate. So if we just take the output of the NOR gate and put it through a NOT gate, we should be able to get an OR gate, right? So if we just take the NOR gate we just had and give the output of that to a NOT gate, we'll basically get an OR gate. So we just invert the result of the NOR and chain them together. And then we can satisfy this truth table here, which corresponds to OR. So next, let's think of a NAND gate. And in this case, so in the OR gate, we had, in the NOR gate, we had parallel or serial on the top and parallel on the bottom. But in this case, we have parallel on the top connecting to positive and serial on the bottom connecting to ground. So, so in this case, we have this truth table, right? And this truth table always returns 1 except for when A and B are both 1. when A and B are both 1, the output is a 0. So how can we possibly get an output of 0 out of this circuit? The only time that the output of this circuit will be 0 is, or the only time that the circuit will connect to the ground is when both of these serial gates are closed. And the only way they could be closed is when both A and B are 1, because these are N-type gates. So because these are N-type gates, A and B both need to be 1 for them to close. And in all other cases, even if one of A and B is 0, this serial structure here won't be closed, but one of these parallel gates will be closed, and the positive voltage is allowed to reach the output. So this is how we can construct a NAND gate. And it's pretty similar to the NOR gate, except we switch up the serial and the parallel, because that allows us to get the opposite result. And in the case of the NOR gate, the only time we got a 1 was when both of them were 0. But in the case of the NAND gate, the only time we get 0 is when both of them are 1. And so we can follow the same logic as last time. In order to create the AND gate, we just take our NAND gate, add the inverter, and boom, we have an AND gate. And so from there, we could move on to, so we could kind of abstract those circuits out. So instead of writing all our circuits in terms of transistors, which would, it just looks kind of messy, and it would be time consuming, we could instead just write them as these symbols here. So in the case of a NOT gate, we just have, we have this symbol. In the case of an OR gate, it's this. This is a NOR gate, this is an AND gate, and this is a NAND gate. And the circles that you see here denote negation. So you see how this is an OR and this is a NOR. It basically negates the output of the OR gate. This circle negates the output of the AND gate. This dot, that's basically a negation here too, because it's a NOT gate. And this is just some terminology. So when I refer to complement, it means the opposite value of X. And a literal is just a Boolean variable. So a literal is just defined as X, and its complement is X bar. And yeah, that's basically all we need to know for this, for what we're learning today. So these AND and OR gates are not limited to 2 inputs. So we could have more than 2 inputs. So if we're feeding in 3 inputs into a gate, we could basically view that as splitting up the gate into 2 gates of the same type. So if we have this AND gate here, it's taking in 3 inputs here, but we could just kind of feed in A and B into one AND gate, and into the second AND gate we could feed in the result of this and C. And it's up to you. You could choose what you want to feed in that way. But here we feed in the result of A and B, but here we feed in the result of B and C. It's the same concept. And so that's how we could have multiple inputs. We could kind of just chain all these AND gates or OR gates together. And basically for an AND gate, we know for an AND that if all the inputs are 1, then the result will be 1. And for an OR gate, the result will be 1 if any of the inputs is 1. And you could do a similar thing for NAND and NOR. So let's talk about logical completeness for a second. So we can actually implement any truth table with just AND, OR, and NOT. So I have this example truth table and the example circuit here that corresponds to it. And let's just kind of go through it and take a look at how it actually does correspond to this truth table. And we're just going to verify that it corresponds correctly. And so what's happening here? We have three inputs, A, B, and C. And both of these, and all three of these inputs are being given to these two AND gates here, right? And then the output of the AND gates is going into this OR gate to get a final result stored in D. So this is our truth table. And okay, so let's look at the circuit a little more. You see that we have these dots here, these circles, and the circles actually mean negation. So whatever A is, the negated version of that is fed into this AND gate, and the negated version of C is fed into this one. And in this case, the negated version of B is fed in. So, and we know that once the inputs go through both of these AND gates, if either of the outputs is 1, the result of the OR gates will be 1, right? So now let's take a look at this truth table. So the only times that the output is 1 is here in this row and this row. And that's when that's when our inputs are 0, 1, 0 and 1, 0, 1. So these are the inputs. So in the case of 0, 1, 0, okay, so we know for an AND gate, for it to return 1, everything needs to be 1, right? So when we feed in A as 0, it negates it, and A is 1. When you feed in B, it's just 1. And when we feed in C, in this case, the C is initially 0, but it gets negated to 1. And it goes through the AND gate, and the output is a 1, so the OR gate also outputs a 1. And for our other case where we output a 1, 101, well, this part is going to return 0 because everything's not 1. But here it'll return a 1 because A is 1, B is 0, but we negate that and make it a 1. And C was also already 1. And the output of that goes into the OR gate, and it outputs a 1 in the end. So, and in any other case, you can verify that that the output will be a 0. And so we kind of just verified the logical completeness here, but yeah, so we just verified that this truth table and this circuit correspond to each other. And it's just an example of the logical completeness of and, or, and not. And because we use the or here, the and gates, and then we also use not with the circles. So let's take a second and talk about DeMorgan's law. And so if we want to convert an AND gate into an OR gate, we can use DeMorgan's law to do that. So basically, in general, to convert an AND gate to an OR gate, or vice versa, if you want to convert an OR gate to an AND gate, you invert the inputs and the output. So an initial AND gate would just be this section here, right? We wouldn't have the circles. But in our case, we are, so here we're converting this AND to an OR. So we invert the input. So we invert A, invert B, and then we also invert the output. So we invert the output here, and that will essentially turn it into an OR. So if we take a look at this truth table, for these possible values of A and B, after we, you can see that after what we just did, negating the inputs and output, the final value is exactly what an OR gate would return, right? So an OR gate returns 1 if either or both of the inputs are 1, 0 otherwise. And that's exactly what is happening in the result here. So this is how you could convert between gates. And so we're gonna apply this in the next slide here. So now we have another claim, right? So we have the claim that NAND and NOR also exhibit functional completeness. And that means that any gate can be implemented using either NOR or NAND gates. So not even both. We could either use just NAND gates or just NOR gates to implement any gates. And so why would we do this, right? Like, why do we care about that? So when we actually build a chip in reality, it's easier to build one when all of the gates are the same, or most of the gates are the same. But in this case, all of the gates are the same because we're claiming that just using NAND, we can build any gate. So we basically build the chip using just NAND gates, and that's a lot more efficient than building a chip with a bunch of different types of gates. So so to show that this is true, basically if we can construct a NOT gate, an AND gate, and an OR gate with just a NAND gate, we can show that NAND has functional completeness, right? So we already claimed that AND, OR, and NOT have functional completeness or logical completeness. And you could build any gate with these three. So if we can build AND, NOT, and OR gates with just a NAND gate, we can prove that by extension, NAND also has functional completeness. So let's try to do that, right? So what we want to do is first, let's try to build a NOT gate using a NAND gate. So basically what we're doing is for a NOT gate, if we have an input A, we basically just want to return the complement of A, right? And so let's think of what it means to AND A with itself, right? So if we pass in A as both inputs to an AND gate, right? Not an AND gate, to an AND gate, the result will just be A itself. And but if we want to negate that, we can just negate the result of the AND, and that'll give us the opposite of A, right? So basically what we do is we just take our so if A ANDed with itself gives us A, then to get the opposite of it, we just negate the output of the AND. So basically, this is how we could do that. So we take A and we pass A as both of the inputs into this AND gate here, and then we negate the AND gate, and we're able to get we're able to basically do NOT. And we're not really using an AND gate here, we're just using a NAND gate, because a NAND gate is getting the opposite of an AND gate. So if we're passing in A as both inputs to a NAND gate, it basically just NOTs A. So that's how we know how to build a NOT, right? That's the standard symbol for a NOT. And so now that we know how to build a NOT, we could move on to try and build an AND gate. So to build an AND gate, we could just combine. So we have a NAND gate, and we know how to build a NOT gate using NAND gates. So we can just combine a NAND and a NOT to turn it into an AND gate. So basically what we could do is, so we have this part. So we take A and B and feed it into this, this NAND gate here, right? And so that just returns the NAND of A and B. And then we take the output of that and pass that in as both inputs into the AND gate, or into the NAND gate, and that results in the complement of it. So basically we took this, whatever we created here, and kind of just put it over here. So we just take the output of NAND and then do this to it, and which is equivalent to knotting it. And that results in an AND gate. And so for OR, we actually have to do a little bit more thinking. So in the case of OR, whoops. In the case of OR, we take two inputs A and B, right? And we need to return whatever the output would be based on OR. So what we could do is, we just talked about DeMorgan's law, right? So we take the inputs and we negate them. And then we take the output and also negate that. And that's how we can get an OR gate. So basically what we're doing is, I'm just using the standard notation for a NOT here to say that we're taking the NOT of A and B, but that can just be replaced with this NAND gate notation here. But basically we take the inverse of A and B and we feed it into this NAND gate, and feeding it into a NAND gate is basically the equivalent of taking an AND gate and inverting its output, right? So what did we do? We took an AND gate. If we just look at this part, we inverted its inputs and we inverted its output. And we just talked about that. If you invert the inputs and the output of an AND gate, you get an OR gate. So here we do exactly that, and the result is an OR gate. And so here we use the NAND gate, and here we also use NAND gates because we could build a NOT gate using NAND gates because we know how to do that. So now we just showed that we can that NAND is functionally complete, and we could do a similar thing with NOR, and yeah, so you guys could kind of think about how that would work, but that's how we show that NAND and NOR have functional completeness, and any other gates can be built using either of those two. And this basically is just a table that shows how NAND and NOR are universal gates, because we basically just showed how to create this. So we basically did this right side of the equation using our gates here. And so that just shows the universality of NAND and NOR. And yeah, that's basically all I have for today. And yeah, so that's just a quick introduction to circuits, transistors, logic gates, all of that. And it's pretty cool how you could just use a NAND gate and build all of any gates you want. So that's all I have for today. And will PA6 involve determining logic circuits? PA6 will involve circuits. So I'm not sure exactly what PA6 is going to look like, but when I took the class, we basically took inputs and returned the output based on different conditions, or like what other command line arguments were passed in. Yeah, so since classes end on Monday, this is the last recitation, and after that we all have finals. So I guess this is the last time I'll be seeing you guys until, I don't know, whenever. So I'll stop the recording now, and it'll be up later tonight, and I'll have the presentation up too.